So we're solving logs. So when I look at this, when I see log base 9 of x plus log base 9 of 3, they're both base 9, so it screams, put me in the picture every time. Okay? So we have log base 9x, log base 9 of 3, so we can put them together because they both have same base and plus 1s in front. There's going to be two ways we can do this. Shh. So we're going to do the first way on the left. So I have log base 9 of x plus log base 9 of 3 equals 1. And then because they both have plus 1s in front, I can put it together as log base 9 and then multiplication. 3 times x equals 1. So I basically have log base 9 of 3x equals 1. Now what do I have to do?
Get the x out.
Yeah, how do I get the x out? When it's locked beside the log or it's locked in the base, what do I have to do every single time?
Oh, go back and no. Differentially.
We're in the same unit as exponentials. Why are we in that unit? Because you have to convert it to exponential. If the x is locked beside the log or the x is locked in the base of a log, the only way you can solve this now is converting to exponential. Same thing with exponential. When the variable is locked in the exponent, the only way I can solve that is converting to a log or a log base 10 both sides, right? So I have to convert to a log. So I get 9 to the 1. Base of my log becomes base of my exponent. What's with it doesn't stay with it, so friends change. So we get 3x. Divide by 3. And x equals 3. So we're doing the first way to do all of the logs first, and then we're going to come back and do the other way. Now we always have to check for extraneous roots. Beside a log and in its base, I can't have negatives or 0. So when I plug it back in, I go log base 9 of 3, that's fine. And I can check these. Log base 9 of 3 is a half, log base 9 of 3 is a half plus a half is 1. This one's good. Okay? So we're going to do the same method every single time where we get all the logs together on one side, anything without a log on the other, and then convert. So then we're going to flip over. So same thing here. All the logs on the left. So now I have a 1 in front and a 1 in front, so I can put them together because they're both like log base 5 with 1s in front, correct? So I'm going to get log base 5. Whenever they're the same base, it screams put me together. And if they don't have a base, you put base 10 so that it does scream put me together. Okay? So I get log base 5, and they have plus 1s in front, so they're going to get multiplied. X plus 1 times x minus 3 equals 1. And then I convert. So I get 5 to the 1 equals x squared minus 3x, what the heck, plus 1x minus 3. My brain stopped in the middle there. So I just expanded what was in the brackets, right? And what do I have to do whenever I have an x squared? Grade 11 taught us this. Get everything to one side, set it equal to, and then factor. Yep. So we're going to get 0 equals x squared minus 2x minus 8. Then I say what times what equals negative 8. What plus what equals negative 2. I get negative 4, positive 2. And the catch with this is I can go right to brackets because it has a positive x squared, right? Like just a 1 in front of the x squared, so I can do product sum. I don't have to do decomp. So I get 0 equals x minus 4, x plus 2. So x equals negative 4, and x equals, positive 4, and x equals 2, negative 2. Now what you have to do is always check and see, left side equals right side, correct? And you have to check and make sure that no negatives are in the base or beside the log. So if I plug this in, I get log base 5 of 4 plus 1, and then log base 5 of 4 minus 3. Well, log base 5 of 5 is 1, and log base 5 of 1 is 0. So 1 plus 0 is 1. So this one's good. Then I try -2. I get -2 plus 1, which is -1. Can I have a negative beside a log? No. So some people just immediately think the negatives are extraneous. A lot of the time they are, but you have to check, because if it was like 4 plus x and you had -2, 4 plus -2 is 2. That's totally fine, right? So you do have to check and see. So this one we circle it, we put a line through it, and we say extraneous. Now this says solve, does it not? So could we not y1, y2 that and see where it intersects and check it? We can always do that with solving. It doesn't matter what unit we're in. It doesn't matter what course we're in, right? As long as we have a graphing calculator, we can check it that way. Okay, we're going to look at this one now. If logs don't have bases, please put base 10. It will give you a much better chance of seeing that you can put them together. When they don't have all the same base, like screaming at you, it doesn't scream, put me together. So I put base 10s on all of them, and I'm like, these are all base 10. I'm probably going to have to put them together, right, when they're all the same base. So we're going to do the two methods again, but we're going to do the first method first. So I have to get everything to one side, right? So I would get log base 10 of x minus log base 10 of 15 minus log base 10 of 0.2 equals what? 0. Then I can put them all together, right? So I get log base 10 of x all over 15 times 0.2. Now the reason why the 15 and the 0.2, 0.2, are in the denominator is because the log 15 has a -1 in front, and the log of 0.2 has a -1 in front. And when they have -1s in front, they go to the denominator and get multiplied. Positive 1 in front, they go to the numerator. Remember with our log laws. And it's going to equal 0. Then I get log base 10 of x over 3 equals 0. Because 15 times 0.2 is 3. It's 15 times 1/5. Then what do I have to do? When the x is beside the log or the x is in the base, I have to do what when I have a single log? Yeah, exponential form. So I go 10, the base of my log becomes the base of my exponent. What's friends doesn't stay friends. So I'm going to get an exponent of 0 equals x over 3. What's 10 to the power of 0? 1. I'm going to multiply by 3. So x equals 3. Then I check it. I can put a 3 in here, and then I'm going to go x to the 3 minus x to the 15, and it'll get me the same thing as log 0.2, so it works. Okay, next page. Because we're going to do, there's two different ways you can solve this. And you might have, like, Sam did it this way, and Susan did it this way. Who was right and who was wrong?
They're both right, though.
No, because they can make a mistake, and if you don't know how to do that way, you're not going to find out where they made a mistake. So they'll say Sam or Tom and Susan, whatever, solve this. Tom was correct, Susan was not correct. Tom was incorrect, Susan was incorrect. Tom and Susan were both correct. Tom and Susan were both incorrect. All right. Oops, got a little. Okay, I want you guys to try this one on your own. So we're going to get log base 3 of x plus log base 3 of x minus 1 minus log base 3 of 6 equals 0. And then we get log base 3 of x times x minus 1 all over 6 equals 0. Then I convert, I get 3 to the 0 equals x squared minus x over 6. 3 to the 0 is a 1, multiplied by 6. So I get 6 equals x squared minus x. So 0 equals x squared minus x minus 6. So I'm going to get x minus 3, x plus 2. X equals 3 works. X equals -2 doesn't, because when I plug it back in, I get -2 here or -3 beside the log, which both would be a problem. So it's extraneous. All right. We're jumping past this one, and we're going to go to this one. So this one, what's the catch with this one?
Got 2 in front of it.
It's got 2 in front of it, so you're going to have to bring it up, then put them together, right? So try this one out. It says to 2 decimal places. What's that a hint?
So
It's going to become the quadratic form. Yep. So we're just doing this one way. So you can take up this space. Log base 3 of x squared minus log base 3 of x plus 3. So we get log base 3 of x squared over x plus 3 equals 3. Log base 3, nope. Um, 3 to the 3 equals x squared over x plus 3. And then we get 27 times x plus 3 equals x squared. X squared equals 27x plus 81. X squared minus 27x minus 81 equals 0. This is my A, my B, my C. So x equals negative a negative 27 plus or minus the square root of negative 27 squared minus 4 times 1 times negative 81 all over 2 times 1. So 27 plus the square root of 7, 27 squared. One of them is x equals 29.72, and then the other one is negative 2.72, which is now this is the other method, which we're going to go back and do on a few of them. So we have log base 4 of x plus 1 minus log base 4 of 2x minus 3 equals log base 4 of 8. You see how I have some logs on one side, some logs on the other? I can just keep it that way. So as long as they're all logs, I can keep it that way. So I could go, and I can move that log over if I wanted to. So I could even go log base 4 of x plus 1 equals log base 4 of 8 plus log base 4 of 2x minus 3. I find it easier when they're added so I don't have any divisions locked in my logs, right? I just moved that log over by adding it. And now I have all positive logs. Literally just added it over. The faces are all looking scared. I just added the log over, right? Nothing crazy. I just took this negative log and added it. All I did. The reason why I did that is because I like having, if I keep it the way it is, I'm going to have x plus 1 over 2x minus 3 in a single log, which isn't a big deal. But people find it easier if it's not like that. So I just added this one over. Now I put the logs together on each side. So this one's going to be log 4x plus 1. And this one's going to be log base 4. And instead of division, if I would have left on the other side, it's now going to be multiplication. 8 times 2x minus 3. Then I get log base 4 of x plus 1 equals log base 4 of 16x minus 24. Now if I gave this to you somewhere randomly on a paper and I said log base 4 of 7 equals log base 4 of x, what would you tell me if that was a true statement? X equals 7. If this is log base 4 of 7, this is log base 4 of x, well then x would have to equal 7, would it not, in order for that to be a true statement? So same thing here. If I get a log on one side and a log on the other, log base 4 of this has to equal log base 4 of that, doesn't it? So now I can just write those equal. Those would have to be equal if this equal statement is true. If I have log base 4 of something equals log base 4 of something, those somethings have to equal. That's a true equal equation. So people are like, I just drop off the logs. No, you're not actually just dropping off the logs. That's not actually what you're doing. You're setting what's beside the logs equal because that's a true statement. X plus 1 has to equal 16x minus 24 if these log base 4s, if this is a true equation. Excuse me. So then we're going to get x plus 1 equals 16x minus 20. You have that already. I've just ran out of room, so I'm writing it back here. So I'm going to subtract 16x. So I get negative 15x plus 1 equals negative 24 minus 1. Negative 15x equals negative 25. Divide by negative 15. And x equals 5 over 3. So you can always skip this method if you don't like it. If you don't like this method, you can always move the logs all to one side, set it equal to 0, and convert to exponential, correct? But you need to know both methods because on a test, if they say Sam did it this way and Susan did it this way, who's right, who's wrong, you'd be like, well, Sam's wrong, Sam's an idiot, didn't do it the way I wanted him to do it. Well, that doesn't work because Sam might be the right one, and the other person might have done it wrong. Okay?
You should just figure out if the person did it your way is correct or incorrect, and then based off of that.
Nope. Because it will be Sam is correct and Susan is correct. Sam is incorrect, Susan is correct. Sam is correct, Susan is incorrect, they're both incorrect. So how, if you just know Sam's correct and you know nothing about Susan, how are you going to narrow that down? You're still going to 50-50 guess at that point. Okay, so the other way, the one method was to get everything to one side, number on other, or all logs to one side, 0 on other, and convert, correct? But the method we just went over is they were all logs. Yes? Well, I don't have all logs. I have log base 9 of x plus log base 9 of 3. Now I need log base 9 of something so that this 1 can go away and be a log. It needs to be log base 9 because they all need to be log base 9 because the other ones are log base 9, right? What can I put here?
9.
Why? Because log base 9 of 9 is 1. So I'm literally just replacing this with this. Log base 9 of 9. Because log base 9 of 9 is 1. Then they're all logs. Right? So I do log base 9 of x times 3, because those are being added. And then I get equals log base 9 of 9. Now if this is true, then this has to equal this, does it not? If log base 9 is something equals log base 9 is something, is it not true that those somethings have to now equal? So now I have 3x equals 9 and x equals 3. Exact same answer. Making them all logs just makes you not have to convert to exponential. That's all it bypasses. Okay, and we're going to perform. So this one, I have log base 5 of x plus 1 plus log base 5 of x minus 3 equals log base 5 of what? I need to get this to be a 1. So once again, this is going to be a 5. Oops, I probably made a highlight. This is going to be a 5. Is it always equal to 1? No, sometimes it's equal to 2, sometimes it's equal to 5, sometimes it's equal to negative 1, right? Like, so you have to pick what it makes it. So, the other way you can do this is you can go 5 to that power. 5 to the power of 1 is 5, right? Because that's what we're essentially doing. We're saying, what can I make this be in order to get a 1 out? Well, 5 to 1 is 5. So now I put them together. So I get log base 5 of x plus 1 times x minus 3 equals log base 5 of 5. And then I get x squared minus 3x. Now these equal, right? So I get x squared minus 3x plus 1x minus 3 equals 5. Then I have to get to one side. X squared minus 2x minus 3 plus, or minus 5. X squared minus 2x minus 8. So ultimately, in the end, you end up in the same spot, though, right? Like look at this. This ends up being same quadratic in the end, no matter which root.
No matter what, left side is, let's say, like both equations are going to have to use the same answer, right?
Yeah.
No matter what. So back to this, if both are correct. So if you could check out just one side, make sure it's correct, and just look at the answer.
If it's like who's right and who's wrong, yes. If it's where they're wrong, problematic.
Yeah.
However, there is a little bit of a cheat you could get through. I wrote these wrong. Talking to you and writing them wrong. So you could go y1, y2, get an answer. 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 And when the answer doesn't match, that's the wrong step.
Okay.
So whenever it's a solving step one, you can really bypass any type of knowledge because you have a calculator. You could technically y1, y2 the question, y1, y2 the first step, y1, y2 the second step, y1, y2 the third step, and like find out where they intersect. And the moment the x value of intersection is wrong, that's the step they screwed up in. So here I get x minus 4x plus 2. So there are ways around it, unless there's variables, and then you can't type it in, and then you have to map it. So we always learn the math because that's just a double checking method, not the way you should go. So does that make sense, how we can do the either method? If I do not give you, Sam and Susan did it this way, which way do you have to use? Either one. If it's a written response, do which one is best for you. I'm showing both because of the Sam and Susan, but I'm also showing both because I want you to pick which one you like better and just do it. Right? Okay, your homework is page 413, numbers 6 and 8. The same page as yesterday. So on Monday, what we're doing is we're doing the log word problems, which is not very many. And then we're doing review questions. Tuesday, first half is review questions. And then radical unit. And then Wednesday, first half questions, radical unit. I'm posting the logs and exponent podcast review for this weekend. Okay, so you can try it.